let's take a look at some best practices that may help you when you're implementing DynamoDB solutions. The first is something that we saw a little bit earlier with the device ID and time and so on. So imagine that you're trying to store time series data, okay? And so a good example of this is event logging. So with time series data, you're capturing something that happens at a given time, okay? And generally, it tends to run from very hot data, meaning it's very valuable, very useful, and over time, the hotness, the temperature of that data tends to decrease. So the latest data may be the hottest, and the oldest data will be the coldest and the least useful. And so one of the things that you should design for is not to mix hot and cold data. Why? Because with Dynamo, you have the ability to assign specific throughput capacity requirements to a table. And so if you have data that requires a high level of throughput, you can create a table that supports that. If you have older data that requires less, you can have a table with lower requirements. This translates to lower cost. So you're cost optimizing based on the mix of data that your application needs to support. Let's go on to the second scenario, and that is, how do you optimally query for large items? So we'll use a messaging app as the use case here. Messaging apps are popping up everywhere, either standalone messaging apps, or it could be part of a social network, it could be part of an online game, and so on. Okay, so let's take this use case. You have a messaging platform, and you want to display the inbox. And so the most obvious way to implement this is to have a messages table. The messages table will contain the subject, the recipient, the sender, and the subject body. And so now, when we want to display the inbox, we issue a query such as this. This happens to be SQL, just using this for example, but this is not how you issue a query in DynamoDB. But basically, you issue this query, select all the messages where the recipient is David, and limit by 50, order by date descending. Okay? And then you do something analogous for the sent items table. Okay? So pretty straightforward. Now, here's the table, the messages table. It has a partition key of recipient, and it has a sort key of date. Imagine that each item is 256 kilobytes. And you want to show 50 items in the inbox and 50 items in sent items. Okay? So what does that translate to? That translates to about 1,600 RCUs per user every time you want to display the inbox or sent items. 1,600 in and of itself is not a big deal, but at scale, that could turn out to be a lot of RCUs that you simply don't need. Why is that? Well, when you display an inbox, you just want to show the metadata to the user, and the subject the message body is not really required until they click on it. When they click on an email message, you can then go fetch the actual message body and display that. But the way that the table is organized now, the message body is one of the attributes of that table. So every time you do a read, you're doing a read for the entire item, including the message body, which you may or may not need to show. Okay? And so what we do is we can partition this table. And this is a technique that's been used for years for relational databases as well as other NoSQL databases. And the idea here is to separate the large attributes from the smaller ones. Okay? So now we have a messages table that contains the message body as well as all the other attributes, but we have an inbox GSI. Okay? The inbox GSI just contains the metadata for a particular email, including recipient, date, sender, subject, and then it also contains a message ID, which will index back into the actual body of the message. Okay? So now we can display the inbox by basically using one RCU or a few RCUs, way less than 1,600 RCUs. Showing how the GSIs look in DynamoDB. Again, pretty straightforward. You set up inbox and sent items. You specify the partition key, the sort key, and then the attributes that you want projected. And DynamoDB basically creates a parallel table for you. And so now when you want to display the inbox or sent items, you query the inbox GSI, or you query the sent items GSI. Items, again, pretty straightforward. You just simply select all the messages where the sender is David, limit by 50. So now, this is a much better way to model your messaging application than what we had before. So here we have a main messages table, which contains the largest items. The lesson here is that you want to distribute or basically separate your large items or attributes from the smaller ones. When you do this, you can save a lot of RCUs, and GSIs will help you model the sort of the many-to-many relationship that you saw here. The scenario that we'll use here is multiplayer online gaming. So imagine that you have a games table which is partitioned on game ID. And so what I want to do is I want to see all the games where Bob is the opponent and where the games are in progress. And so with this table, that query becomes a little bit more complex than it needs to be. The issue here is that with Dynamo, it provides a partition and a sort, but if you wanted to query for some other items that are not part of the partition and sort, how do you do it? And how do you do it efficiently? Well, the answer again is to use a GSI. And here what we'll do is we'll create another table where we have opponent as the partition key and date as the sort key. So now we can get all the items where Bob is the opponent, right? And then we can just filter out the ones that we need. In this case, what we want to do is we want to filter on status, where status equals pending. Okay? And this works pretty well. When we use this technique, what happens is the filtering happens on the Dynamo side. And so Dynamo read 3 items. You'll be charged for 3, let's say, RCUs. But it filtered out one of the items, the third one in this example, and it only sends back 2. So it sends back less data. It'll simplify your application code because it's less filtering that you have in your code. Here, we have a very simple example. But imagine that this query generated, instead of 3 rows or 3 items, it generated 3,000. And then it filters out to maybe just 300. So in terms of efficiency, if your index isn't entirely selective, you may want to use a different technique, and that is the composite key. With the composite key, what you do is you take 2 attributes, in this case status and date, and you concatenate them into a new attribute known as status date. With status date, what we have is a secondary index, very similar to the one we saw earlier, where we have opponent as the partition key, now status date as the sort key. Now with this in place, what we can do is we can issue this query that says, give me all the games where Bob is the opponent and status date begins with pending. Okay? This will give us exactly the data that we want. And so the reason it does that is because, well, the status is sorted by state, and then it's sorted by the actual date itself. Another feature you may want to take advantage of is sparse indexes. So imagine that you have a game scores table. Out of those millions of items, which are gamers, there's a small subset who have received awards. And you need to display all the users that have received awards. If you just had this table, that would be a very tedious thing to do, because you simply can't filter on awards by itself. Okay? So what we recommend is that you create an awards GSI where the partition key is award. When you do that, the GSI will only contain the items where there is a value for the attribute award. So it's a sparse index. So now when you want to show all the users that have won awards, you simply scan the awards GSI, and bam, there you have it. So it's a very efficient way to get at that data. You can certainly filter, use the filter operator to get at data that may not be in a highly selective index. You can take advantage of composite keys and concatenate 2 attributes to get a composite key that can give you much higher selectivity. Okay? And use either of these techniques when you want to optimize the query as much as possible. Earlier, we talked about the problem of heavy reads. What about heavy writes? So imagine that you're going to implement an app that may be supporting an election, or maybe you're supporting a game show where contestants are voted on to be the winner. Now, here's what your DynamoDB tables look like. You have many different candidates, but as with any election, you have a number of candidates, but usually only a small subset of them will actually get the majority of votes. So here we have a table that is provisioned with 200,000 write capacity units, okay? But what we're seeing in reality is that all the votes, nearly all the votes, are going to two candidates. Candidate A is getting 70,000 writes per second, and candidate B is getting 50,000 writes per second. The rest are not seeing much action at all. So what do we do about this? Well, we're going to use a well-worn technique that has been proven to scale to billions of writes per second, and that is basically write sharding. With write sharding, instead of writing to a single table, you'll write to many tables. So in the case of candidate A, you can create a small set of tables for candidate A. So when a vote comes in for candidate A, what your application will do is it'll select a table for candidate A based on a random suffix. So the random suffix in this case is going to be a range of numbers from 1 to 8. We'll already have tables that span for candidate A from 1 to 8. And so your application will pick a random table. It'll write to that table. And then if you provision enough write capacity units for all these tables, you can easily support a very high level of throughput for that particular candidate. And you can do the same thing for other candidates as well. So this will enable you to scale the writes to a huge level of throughput. The caveat here, though, is that now your reads become a little bit more complex. That's because with any sort of voting system or any scenario like this, you want to know at any given time who's the leading vote getter. And so if you had a single table, that's easy to figure out. But now you have multiple tables. And so what you'll need is a process that will scan. This is sort of a scatter-gather technique where it'll scan a bunch of tables and aggregate that data into a table such as the votes table. Okay? And so you need to do this periodically so you can get real-time updates. But basically what you're doing is you are trading off read cost for write scalability. And this is important because if you go back to what we talked about earlier, when you provision WCUs, it is for the entire table. It's not for partition, per partition. It's equal among the partitions. Okay? And so if you're seeing a hot partition when it comes to writes, you'll have to use a technique such as this to mitigate that and ensure that your tables can support the writes that you need. So those are some of the techniques that we've seen work again and again with many of our customers. And so definitely take those into account when you're designing your DynamoDB applications. So with that, let me dive into a feature of DynamoDB that enables a whole bunch of other capabilities, and that is streams. With DynamoDB streams, you get a change log of any modifications to your table. These modifications are captured in the stream. They are asynchronous, so whenever a change is made to a table, it's captured asynchronously in the stream. The change is captured exactly once, and it is strictly ordered at the item level, okay? And the change is available to you for 24 hours to read and process and do with it what you would like, okay? You don't have to worry about the durability of the stream or the scalability of the stream. It's all taken care of for you by Dynamo and Kinesis, which is a product you may be familiar with or not. But essentially, the streams are using the Kinesis as the underlying mechanism for capturing the changelog data from the table. And generally, you're going to see sub-second latency in what appears in the stream when a change is made to the table. Now, when you set up streams, what you'll have to do is you have to pick a view type. A view type specifies what data is captured in the stream. So do you want the old image and the new image? Do you just want the old image? Do you want just the new image? Or do you just want the keys? The reason why this is important is when you read the stream, you're going to be charged a read capacity unit. And so you don't want to read more information than you have to. So if you just want to do replication, you want to create a customized replication application, then you just want maybe the new image. If you're doing something that requires, that's in the audit and compliance field, you may want both the new and the old image. So be careful in terms of what view type you pick, because it can impact the cost to read the stream. How does this all work? Well, as a DynamoDB application is making changes to your table, those changes are going to be captured in the stream. A stream is made out of many different shards. We use sharding for a number of reasons, for scalability, for durability. And then the data in the shards are going to be available to you for 24 hours. At this point, you can read the stream using the DynamoDB Streams API, or better yet, you can use a Kinesis client library worker to do that. The Kinesis client library worker is sort of a higher level way to deal with streams. It provides a number of features, such as the ability to do checkpointing, so that if the process reading the stream dies, when it comes back up again, it can pick up where it left off. So it does do a little bit of state management for you. One of the things that Streams enables is replication. And we provide a replication library for you that's available on GitHub. So if you wanted to do your own custom replication, you can start there. Okay? Or better yet, if you simply want to replicate DynamoDB to another region or multiple regions, we have a CloudFormation template that you can launch. It'll launch a EC2 instance. The EC2 instance will present a replication console. You can configure it. You can specify which table you want to replicate and to what region. And then it'll do the replication for you. This is one-way replication, so if your DynamoDB table sits in Northern Virginia, you could tell it to replicate to Oregon or to Dublin or to Tokyo, or all the regions that we support. Okay, all the regions, I should say, that DynamoDB is supported in. Okay, and so this is pretty straightforward. And if you wanted to do multi-master replication, that's something that you can implement yourself via the libraries that we provide. DynamoDB also integrates with Lambda. So with Lambda, you get the ability to specify code that's executed without having to deploy any infrastructure yourself. So Lambda today supports Java, JavaScript, as well as Python. And as long as you can express what you want to do in any of those three languages, you can basically get a DynamoDB stream to interact with that and do whatever you want. So in this example, all we're doing is whenever a stream item is available, it calls a Lambda function, and the Lambda function simply displays the item that's in the stream. So the idea is that you can replace that with any code that you want. And when you do that, you can get things like triggers. So DynamoDB supports triggers, and it uses Lambda to implement that. So with triggers in place, what you can do is when a change happens to a table, that change is captured in a stream. That stream will invoke a Lambda function. The Lambda function can then be used to create things like a derivative table. So for example, if you had a JSON attribute, you may want to index the JSON document on items that are not at the root level. And so you can use the Lambda function to do just that in a derivative table. Okay? You could also use it to update your cache. Earlier, we talked about using caching as a way to alleviate a huge amount of reads, unnecessary reads to DynamoDB. So if a product gets updated, well, you can trigger so that the cache gets updated with the latest product information. Okay? You can also keep your search indexes up to date, and you can also call out to external systems. You can send an email, send a text, or you can trigger a workflow. You can do pretty much anything you can do as long as you can specify it in code. So with that, what I'll do is I want to wrap up by talking about an emerging architecture that has been made possible by the continued maturation of the services that are part of AWS. And that is what we call serverless event-driven applications. The idea behind this is that today, it becomes very possible to create very sophisticated applications without managing any infrastructure. So what this means is that without deploying EC2 or RDS and having to think about the size of EC2 instances and how much memory, how much RAM, and EBS, and all this other stuff, and thinking about auto-scaling and load balancing, you can do away with all of that and use services that automatically scale, that have durability and availability built in. Okay? So this is an example of an application created by some SA colleagues of mine. It's a survey form application. it uses, for example, S3. S3 has the ability to host web pages. So the front end of the survey is an HTML page written in a modern JavaScript framework, such as Angular or Ember or Bootstrap. And so it can do a very sophisticated UI, but even better, it can make callbacks to back-end services. In this case, we're calling into API Gateway. API Gateway can call into Lambda. Lambda can execute functions and code. And then in this case, what we'll do is we'll take survey data, process it, and then store personally identifiable information into S3 in an encrypted format, and then non-encrypted or non-PII data into DynamoDB. Of course, you can do the same thing if you want to store confidential information in DynamoDB. You can simply do that by encrypting the data via Lambda before it gets stored in Dynamo. Now, what you're seeing here is the ability to have applications that require no servers. Okay? So that means it's less administration, less patching, less upgrades, and less administration on your part. And it makes the life a whole lot easier. And you're going to see more and more examples of this emerge over the next few months and years, because there are going to be more services that are going to require really no services on your part to maintain. And Dynamo is going to be a central part of that, because unlike other databases, like relational databases, Dynamo is accessed via APIs. Okay? And these APIs can be called from a web page. So you can have a web page that simply stores data into Dynamo directly without going through a web server, for example. Okay? So Dynamo is directly accessible wherever you can make a HTTPS call. And we have client-side JavaScript applications and SDKs that can help you with that. Okay? So this is a new emerging paradigm. And Dynamo is a core part of that. And hopefully, with today's session, you understood some of the basics of Dynamo and some of the use cases and how to optimize for particular scenarios that you may encounter.